In this segment, I'm going to talk about the goal seeking with delay archetype. This is essentially the standard balancing loop with one slight change. Slight change in structure, though, as you'll see, with an enormous impact on the way that it behaves. It's possible that between the time that the action happens in the structure and the time that the current state actually changes, there could be a time delay, or between the time that the current state changes and that change is actually realized, there could be a time delay. And that has an influence on the behavior of the structure because it's essentially causing one to act without really being aware of the current state of things. So that if I take action and change the current state and I don't realize the extent to which the current state is changed, when I take the next action, I'm actually acting on outdated information that's not current. So that it's very possible, as you'll see in the simulation in a moment, to overreact to the efforts that I take to attain the goal and actually end up overshooting the goal and then having to act and bring things back to the way that they should be. So if I take this structure and implement it as a stock and flow simulation model, what I've added is an action factor to simply control the extent to which the gap actually influences the action, so that the gap is times the action factor. And this particular flow is set up so that it can move in either direction, so that the action may be positive or negative depending upon whether or not I'm still the current state is less than the desired state, or I've actually overshot the goal and I may have to take away from the current state to get back to where I intended to be to begin with. And then I've added this delay state, which is a built-in function. It says delay the current state by some time delay, and with a variable called time delay. And this is set up so that I can easily change the amount of delay that's in this part of the structure. Now I said over here that the delay could be in a couple of different places. I've simply chosen to implement it here. You could implement it in other places if that was more appropriate for the actual structure that you're dealing with. Now, as is typically the case, I go ahead and implement this with in a very generic form, so that the actual goal, the desired state, is 1. The current state starts out as 0. And as the action progresses, the current state migrates toward the goal. The gap between the desired state and the current state continues to get larger, and the action declines as that happens. And note that the action was initially set at 0.5. So this is the typical goal-seeking behavior. If I now go ahead and introduce a time delay of 1, notice that the current state approaches the goal and actually ends up overshooting the goal, and then effort has to be taken to bring the current state back to what the goal was intended, or the desired state was intended to be. This happens, as I said, because the information that's being used to decide what the action is old information. If we increase the time delay to 2, notice that the overshoot is even more pronounced, and more effort is applied to come back to the desired state, but even that is overshot in the opposite direction, and you end up with what's called damped oscillations, and it finally reaches the desired state after some period of time. Now, the extent to which this overshoot happens, it has a lot to do with the value of the action factor, how intently one is attempting to reach the current state. And later, when you actually interact with this model and change these values, you will get a better sense of how the various factors impact. Continuing along, if I go ahead and set the time delay to 3, I end up with a situation where the environment oscillates back and forth, and I never end up achieving the goal. Imagine the extremely impatient person in the shower who is constantly turning the dials back and forth, and because they're not waiting to see the result of their actions, because they're so impatient, they'll never get the water temperature to a desired level. They will just constantly oscillate back and forth. There are times when being impatient is not a very useful characteristic. And even with a longer delay, you can end up with a situation where the behavior is actually out of control. So someone says, well, how can the delay be such that you don't know what the current state is before you act? And the extreme example that comes to mind is, consider controlling the Mars rover from Earth, looking at a picture that's 9.5 minutes old, giving a command to the rover, which takes 9.5 minutes to get there, and another 9.5 minutes for you to see the implications of what you told it to do. So you're actually 18 minutes out of sync with what's going on. So it could be very easy to overreact. And that's an extreme situation, though the extent of the delay that's relevant depends upon the delay in contrast to what's changing. I mean, there could be situations where a millisecond delay could be relevant to the action taken to change the current state. It really depends upon what the specific situation is that you're considering. Though what this structure points out is that it's very easy for a very simple structure to have a behavior that's extremely not intuitive because of the way that the relationships unfold over time. It provides a sense, I think, of why simulations are so critical to get a real sense of the implications of a set of relations which are unfolding dynamically over time, especially if there are delays in the structure. I mean, imagine a half a dozen different reinforcing and goal-seeking loops interacting simultaneously with multiple delays in the structure. I mean, it's just beyond the human capacity to intuit the implications of how that structure is likely to behave, which is why simulation is such a useful approach or useful tool. Now, if you sense that you're dealing with a goal-seeking with delay structure, there are essentially three approaches to dealing with it. You can attempt to reduce or remove the delay. In some instances, that's possible. In some, it's not. If you're dealing with a situation where you can, in fact, get closer to sensing what the current state is after the action's taken, you can cut the delay out of the system. Though, in the case of the Mars rover that I talked about a moment ago, there's no way to cut the delay out of the equation because it's a nature of the physics of the structure itself. Now, the other one is delay the action until the current state is sensed. What I said about the shower and being impatient, if you know that there's a delay, then you can hesitate rather than act until you're aware of what the current state has evolved to, and then base your actions on that current state. And then the third approach is to actually take smaller steps as opposed to, in other words, if the gap says the difference between the desired state and the current state is 2, the action that you take might be 0.5 to move it in the right direction, though not so much as to overdrive the current state. So there's 3 possible approaches. The one that is most appropriate depends upon the actual structure that you're dealing with. And I encourage you to go ahead and access this model and change the values of the current state, the action factor, the desired state, and the time delay to get a sense of how those factors influence the behavior of the structure. It sort of evolves through experience, so you get a better sense of it. I also say it's a lot like riding a bicycle. You get a better sense of how it behaves by interacting with it, the same way that you only get a sense of riding a bicycle by riding a bicycle. So, hope you found this informative, and I'll see you in the next video. Bye.